All right, well, hey, welcome to the end of yet another week here in statistics. In fact, this is our last class of February, if you can believe it. We're down to just one more month to go. So anyway, so today's plan, after we go over homeworks and all that, is to continue working on looking at comparing two populations. I'll do a little real quick review of a two population hypothesis test using a mean. And then we'll talk about proportions and see how we do those. And then we'll look at what we do when we've got data that's not independent, or if we have what we call matched data. For example, if we want to see how things change with a specific group, we'll see how we can actually do a hypothesis test on them. All right, so that's the plan today, at least that's my plan. But let me go ahead and start by asking you guys, are there any homework sets that you would like to look at? All right, well, it looks and sounds like there aren't any. So I'm going to go ahead and hop up to the whiteboard and we'll keep plugging along. So I'll be with you in just 1 second. All right, so last time we were looking at comparing two quantities and seeing how we do that and using hypothesis tests to see whether or not we believe certain things about those populations. And hopefully you saw that it wasn't really that much more difficult than doing a hypothesis test on one sample. It's just we have to use a different command. We're looking for different things. I showed you the formulas for things like um, the standard deviations and things like that. And they're pretty gnarly. However, with our technology, it's not that bad. We just put in our information and we let it go. So let's kind of refresh our memory on how that worked with this example. So let's suppose that we're curious if colleges and universities actually offer more sports to men than to women. All right, so maybe we think that that's what our what we believe, and so we're going to do a survey to check that. All right, so we believe that universities offer more sports to men. Okay, so we're going to go ahead and we're going to check that. We're going to go see if that's true or not, or if we believe that that's true or not by taking some samples. All right, so we go out and we actually sample 50 different colleges. All right, so we go to 50 colleges and we check it for the men. Right, there were 50 colleges, and we find that there's an average of 8.6 men's sports teams per college or university. All right, so it's a, oh, you got a football team, you got a bowling team, you have an archery team, whatever. We count them up, and we find out that on average, 8.6. Now, from some research that we find from the NCAA, we know that the standard deviation for the population is 3.3. Okay, so this is not a sample. This is just the overall. We know that this is the case. Okay, so then we do the same thing for women. We draw another 50 random schools. May not be the same. Some of them could have been on the same list, but this is just another 50 random universities, and we do the same thing. We find that their average number of female sports teams is 7.9, and again, the NCAA tells us that the sigma here is 3.3 as well. All right, so let's test our hypothesis. And let's just say that we're going to do this at, how about the usual alpha equaling 0.05. So we'll go with the 5%. All right, so let's start by drawing or writing our null hypothesis and our alternate hypothesis. So the null hypothesis. This is one where we want the means to be the same. So I'm going to put here mean with the sub m equals mean with the sub w. Okay, so this is going to be for men and women. So the null hypothesis, as we saw before, is always the equals. So then our alternate hypothesis, this is the one that we're actually thinking. We believe that men have more sports than women. And I'm even going to write that this is our claim. All right, so I strongly recommend you always write those out so that you've got them, so that you know what they are, so that then you can reference them later. Because remember, when we do our test, we either reject the null hypothesis or we fail to reject it. So it's good to know what that null hypothesis is, so we can kind of go back and see. All right, so let's run it. Let's actually do this test. So I'm going to hop down onto the computer and I'll share my calculator screen again. And we'll see what this tells us. All right, so hopefully you can see my calculator. So we're going to do a test. So the question is, which kind? So let's go back and let's look at our stat. We go to stat. We are over to tests. So in this case, we're doing a 2-sample test. And so if you look at all the ones that are 2s, we see a 2-sample Z test, a 2-sample T test, and a 2-prop Z test. Okay, well, it's not going to be a 2-prop because we're not looking at proportions. We're not looking at percentages. We're looking at averages. We're looking at means. So it's going to be one of these. So which is it going to be, Z or T? Throw in the chat box your guess on that. Is it Z or T? So Willie says Z. What about the rest of you guys? What do you think? Z test or T test? Or are we all just going to trust Willie? See if I you throw in other ones in there. Okay, good. So it is a Z test. And why is it a Z test instead of a T test? Yeah, we've got the standard deviation, specifically the population standard deviation. So if you know the population's standard deviation, we get to use a Z test. So we're going to come to our calculator and we're going to arrow down because we're going to do a 2-sample Z test. All right, so let's do it. Now, this one, we're not going to use data because we don't actually have the 50 different results for the men and the 50 50 different for the women, but we do have their stats. So we'll arrow over, hit enter. All right, and so now let's start putting in what we know. So for both of these, we have standard deviations of 3.3. Put those in. Okay, so x1, how about we'll just take them in order that I wrote them there. So we'll have the men's numbers be the first sample and the women's numbers be the second sample. So that means 8.6 is going to be our average for the men. And the number of men's universities we checked were 50. So then x2, this is the women's average, which was 7.9. And we also tested 50 schools. Okay, now those are both equal, but we don't have to have that. Hopefully you remember that when we're creating these, we don't have to sample the same number of people or the same number for each group. It's totally fine if they're different. Okay, so now we're going to go down to our, what do we want to test? So remember, 1 was the men, 2 was the women. So if we look at what our alternate hypothesis was, it was that men is greater, that the mean for the men is greater than the mean for the women. So I need to arrow over and highlight greater than, right? I want mean 1, so the mean for the men, be greater than mean 2, the mean for the women. All right, so I'll arrow down, go ahead and hit calculate, and it spits out some numbers. So remember what it's giving us. The Z, that's the Z-score. That's the number of standard deviations away this result is. And then the p-value, that's the percent likelihood that this would occur, that these samples would show up if the null hypothesis is true. So the bigger p is, the more likely the null hypothesis is to be true. The smaller p, the less likely. All right, well, we get 0.1444. So let me hop back up to the whiteboard. Let me turn off the share and think about what this tells us. All right, so according to this test, we got that P was 0.1444. All right, so in terms of do we, how do we feel about this test? We compare this against alpha, and we see that this is actually bigger than alpha. Right, the alpha right above is 0.05. So we're going to do the same thing that we do if it's a one sample hypothesis test. Since P is greater than alpha, this tells us that we're going to fail to reject H naught. All right, so this doesn't mean that the average number of sports for men is equal to the average number of sports for women. That's not what this is saying. But what this is saying is that we don't have enough evidence to throw that out. We don't have enough evidence to say that they're not equal. All right, so in terms of the context of this, I guess what we would say, we're going to kind of write out a kind of a final summary here. I would write something along the lines of, there is not sufficient statistical evidence to suggest that the mean number of sports for men is greater than women. we don't have enough information, or that the statistics don't suggest that that's actually true. Could it be true? Absolutely. But with our study, it doesn't suggest. Okay, so hopefully this is kind of a good little reminder of how we test for means when we want to look at two different, or how we do a hypothesis test for means when we're looking at two different data sets. Right, two different. All right, so any questions on this one? Is this kind of a good refresher? Give me a thumbs up if we're feeling good. If not, give me some other symbol. All right. Lots of thumbs up. I like this. Okay, so let's turn our attention then to what about proportions? We saw that when we did proportions before, we had to treat them a little bit differently. And so the question is, how do we deal with proportions when we want to do a hypothesis test for two different groups? Okay, well, just like with the means, here's how the proportions really play out. We're going to test these proportions. The null hypothesis is going to be that I'm going to call them A and B for two different sets. No, let's call them 1 and 2. The null hypothesis is going to be that the proportions for the two groups are equal, or alternatively, that the difference in the proportions is actually equal to 0. That's really what we're doing. And I kind of mentioned this when we did means. In terms of the alternate hypothesis, then, it can be any of the other forms with an inequality. I'm just going to go ahead and do not equal to, but we can make it greater than or less than, which again means we're really looking at the difference of them, saying that they're not equal to 0. All right, now in terms of the conditions, what we need to do the test on proportions, we need the following. The first is that they are random. Okay, no big deal. That's what we saw with means. But we need both samples to be random. We also need them to be independent. Right? We can't have one being based on the other. But then the other thing that's kind of weird is that for this, we need n times p be greater than or equal to 5 and n times q to be greater than or equal to 5. Okay, so do you remember what P is? Right, P is our probability of success, and then Q is the 1 minus that. Basically, we need to have a large enough sample size that these numbers are greater than or equal to 5. Okay, that's not that hard to do, but we definitely need that in order for us to do a hypothesis test for proportion. So you can't really do this on a small set. You need to have some fairly good size sets. N doesn't have to be that large for this to happen, depending on your proportion. I mean, think about if it's a 50-50, then this just has to be 10. So it's not that big of a deal. All right, so when we have this, what we actually do is we do a pooled proportion. Now, this isn't going to actually matter to us because we're going to have the technology deal with it for us. But if we were to do this individually, we'd have to do what's called a pooled proportion. And pooled, all that means is you put both groups together. So if you ever see that word when it says pooled, pooled just means that they're put together into one larger group. Okay, so that means that we're going to get a probability. I'm going to call it P sub C, a proportion, sorry, sub C. This is going to be a combined, so I'm using C, proportion. And basically what you do is you take the number of successes from both, add them up, and then divide by the total number that you looked at. Okay, so like let's say for the first proportion, we tested 150 people. And the second one, we did 200. We would add those together to get 350 on the bottom. And from the first group, there were 12 that were in our group, and the other one, there were 38. You're going to take your 12 plus 38 and add them. Okay, so we basically take both of those into one big group. We call that a pooled data set. So that gives us our pooled proportion. And then if we want to calculate the standard deviation, and this is another time when you go, thank God for calculators and computers, you're going to take that PC times that QC. And you may remember that what we did when it was just a regular proportion, we divided by n. Well, this time we're still dividing by n, but it's coming from adding the 1 over n's for both sets. So again, I'm showing you this just so you can see it. You can see how it's different than before and how it's similar to what we did before. But you're never going to have to use this formula, ever. Your technology is going to take care of it for you, so you don't actually have to worry about it. All right, so as long as we've got these conditions, we can go ahead and test these just like we always do. All right, so let me show you some examples, and you'll see that it's not really that much more difficult. You just have to make sure we're using the right commands in our calculator. All right, so here's the first one. Suppose that 15 years ago, a study was done and found that 26 out of 60 families had dogs. Okay, so 26 out of the 60 had a pet dog. Probably. Okay, and so then let's say that this year, a similar study found that 26 out of 75 . All right, so here's the question. Is the proportion different now? And for this, again, we need to have a level of significance. So let's use good old alpha equals 0.05. Okay, so to get back to that idea of the pooled proportion, if we were to do that, let me just show you. Again, we don't need to do this, but if you were to do it, the pooled is found this way. You take the total number of successes. So we had 26 plus 26 over the total number of tested groups, so 60 plus 75. So this would be 52 out of 135. So that's our pooled proportion. You would then use that to get your Q, Q1 minus that. Then you multiply those together, multiply by the 1 over 60 plus 1 over 75, get your standard deviation, blah, blah, blah. Okay. But again, we've got technology that's going to do all that for us. I just wanted to show you what it meant to pool it. Basically, just taking those two groups and sticking them together into one big one. All right. Well, anyway, let's write down our hypotheses then. So our null hypothesis, as always, is going to be that these two proportions are equal. That the proportion from 15 years ago is the same as the proportion from today. Okay, so what's the alternate going to be? What symbol am I going to put between P1 and P2? It's going to go in there this time. All right, thank you, Carolina. It says not equals. So this one's not equals because all we're looking for is the proportion different? Not more, not less, just different. Okay, so this is going to be a two-tailed test. Again, it doesn't really matter because the calculator will take care of this for us. But this is a two-tailed test. I don't care. Are we bigger, smaller? Yeah, either way. I just care. Are we different? All right. And I guess that's really what we're testing, right? So this is our claim. We're claiming that it is different now. Or maybe we're actually claiming that it's the same. But either way, this is what the null and alternate hypotheses look like. All right, let me jump down to the calculator and show you how we do this. Pretty much the same idea. We just have to go somewhere else in on our screen here. So let me share these. All right, so again, we're going to go to stat, arrow over to test. Okay, so now this one we are doing proportion. So we're going to come down and do the 2-prop z test. I'm going to press 6 just to bring us there. All right, so we're testing 2 different proportions. So the first one, so let's say that the first one is the older study. We had 26 out of 60 people, out of 60 families, had dogs. So proportion 2, that's 26 out of 75. And in terms of what we're testing, I want to highlight the not equal, right? Because we're just saying, are these proportions different? Okay, well, up down here, we'll do our calculate. Spits out a number. All right, it actually spits out all kinds of numbers, but let's sort of just go down the list and see what they all are again. So Z, this is the Z score for this result. The P, that's the P value for this result. So you see those guys with the hats, those little caret symbols, we call that a hat. So P hat 1, that's the actual proportion of the first sample. So if you take 26 and divide it by 60, you get this decimal. The P hat 2, That's the proportion for the second sample, so 26 out of 75. And then this one that's just plain old p hat, that's the pooled proportion. If you take the 26 plus 26 divided by 60 plus 75. And then you'll see we got our numbers for the first and the second. I don't think there's anything else for us to see. But there it is. There's our results from the 2 prop Z. So this is why I was saying you'll never actually have to calculate a pooled proportion, because the calculator, your technology, will give it to you. All right. So, yay. All right. But the important number was that p-value. So let me go ahead and write that down. 0.3038. And then we'll talk about the results here. So 0.30, I think it might have been 3848. I actually don't really care at this point, because that decimal doesn't really matter. Again, we look and see how does that compare to alpha. So we were at the 5% level of significance. Again, we see that our p is greater than alpha. So just like that other one, we're going to fail to reject H naught. Okay, so H naught said that the proportion is the same today as it was 15 years ago. And we do not have enough information to throw that away. In fact, think about this, the 0.30, 30% chance. So roughly a 1 in 3 chance that if the proportion is the same, that we would get this kind of a result. Yeah, that's pretty likely. Which is why I'm definitely not confident to say that they're different. All right, so I guess if we're going to wrap this up and write our statement, again, we would probably say there is not sufficient significant, or well, there's not significant statistical information to rule out the proportion is the same today. The proportion of dog owners is the same as 15 years ago. So again, look at the wording. I didn't say the proportion is the same as 15 years ago. I said, I don't have enough information to rule out that. Right. And so again, this is I kind of used the phrase last time. I picked somebody, so I'll pick Willie this time. I'm not saying, hey, Willie, you're right. If Willie says, hey, the proportions are the same. I'm not saying, you know what, Willie, you're right. What I'm saying is, you know what, Willie, I can't say that you're wrong. I'm not comfortable saying that you're wrong. Which is a different statement, but those are the statements that we make when we do hypothesis testing. So if we, let's say we were doing this for some, you know, maybe for some like dog food company or something, maybe they were curious, we would report back to them and say, you know what? It doesn't look like the proportion has changed. I can't say that, yes, the proportions are the same, but I definitely don't have evidence to say otherwise. So there you go, dog food company. Now you know. And then they can make their decisions based on that. All right, so here's an example of a test with proportions. And again, not really that different. Like, think about similarities and differences here. What are we actually doing that's the same and different? We always, no matter what, have to start with an alpha. And we also need to construct our H naught and our HA. Right, our alternative or null hypothesis and our alternative hypothesis. Then we go to the technology. That's where it's different. That's where we're putting in different numbers for a different scenario, blah, blah, blah. Okay, but then once that's all done, we're back to it's the same as every time. We take the calculated p-value and we compare that to alpha. If it's bigger than alpha, we fail to reject H naught. If it's less than alpha, we reject H naught. And so then the consequences are the consequences. So a fail to reject always sounds like this. If this had been a reject, I would have said, there is significant statistical information to reject the idea that the proportions are the same. And therefore, I'm confident at the 5% level that they're different. So again, same thing from top to bottom. We follow the exact same ideas. All right, so here's what I'm going to do. I'm going to have you do one. Actually, I'm going to have you do one just real quick on your own. So hopefully you got a calculator handy. I'll give you a couple of minutes to do this. So let me write up what I want you to test. All right. So suppose that there is a claim that men do not work as much overtime as women. And when I say here that men do not work as much, how about we'll say that claim that the percentage of men who work overtime is fewer or is less than that for women. Okay, so a study found that 7 out of 100 men said they worked OT, they worked overtime. While 10 out of 95 women said they did. I want you to test this at a 10% significance. Okay, so I'm going to give you a couple minutes to do this. And what I want you to do is calculate a P. So I'm going to have you report back what your P is. And then I want you to tell me what you ended up doing with the null hypothesis. Either reject or fail to reject. Okay, so take a minute or two and see what your calculator tells you. All right, so I see that Willie already put his p-score or p-value that he found into the chat. What about the rest of you? What kind of p-values did you find? You guys still out there? I feel like I'm Pink Floyd on the wall. Is there anybody out there? All right, well, I guess we're going to run with Willie's p-value, and let's see if we agree. So let's go stat. Come over here to test. Again, we're going to do a 2-prop Z, that's 6. All right, so we'll make the first one be the men, which is 7 out of 100. And for the women, it was 10 out of 95. Uh-oh. Which of these are we going to do? Are we going to do the, I just realized I wasn't sharing my screen. All right, so we got 7 out of 100, 10 out of 95. So which of the tests? So we never did write down what our null and alternate hypotheses were. I'm going to go ahead and put them up here. I know you might not be able to see them very well on the little screen, but if you switch over to that screen, let's see it. But here's going to be the null hypothesis. Is going to be that the proportion of men is equal to the proportion of women again. And for the alternate, we're going to come back to what the claim is. The claim is that the men is less than that for the women. So we're going to do PM is less than PW. So number 1 was our men. So we need our men to be less than our women. So let's come over here and highlight that one. So we want the men to be less than the women. And then we'll go ahead and calculate. All right, so this is another good reason why you should always do the null and alternate hypotheses first. Because depending on the form of your alternative hypothesis, that will change what you enter into the calculator. All right, so Willie put in the chat box 0.1915. I got the same thing, rounded to the 4 decimal spot. So I think that's good here. All right, so what does that tell us then? Well, our P was less than, or sorry, our P of 0.1915. This is greater than alpha, because alpha is 0.1. So we're going to fail to reject H naught. So basically, there's just not enough here to tell us that that isn't the case. That there isn't enough here to tell us that men and women don't work the same amount of overtime, or the same percentage of men and women work the same amount of overtime. Okay, so hopefully you were able to kind of go through that process. Thank you, Willie, for sharing your numbers. I appreciate that. So at least I know that you were able to enter it in correctly and do it. So I'm going to hope that that's the case for the others. I don't know. All right, so piece of cake, right? Two different groups. Proportions means it doesn't really matter. We just have to make sure we're using the right test. All right, so that brings us then to the last kind of thing that we can do when we've got two different groups. And that's to test matched data or paired data or data that's related to each other. Okay, so I'm going to call it paired data. And it's exactly what it sounds like. It's where our data is coming in pairs. They are linked together by some fashion. And we still want to compare the two groups. Let me give you some examples, right? An example could be maybe weight before an exercise program versus weight after. Right? So maybe we own a gym and we are starting this new exercise program and we want to see, does it actually lead to weight loss? So we're going to have our group of people that are going through this. I guess we have 10 of them. We'll have their 10 before weights and their 10 after weights, and we're going to compare them, right? Or it could be some sort of a, size of cancer, or size of a tumor, let's say, before and after chemo treatment, right? Or so on and so forth. Okay, so this is the kind of thing that we're going to want to use for a pre and post. How are things looking before? How are they looking after? Right? Maybe grades on exams. How were they prior to tutoring, after tutoring? Reading comprehension before, after taking an English class, or So this is the sort of situation that I'm talking about, where we've got paired data, where we're actually going to be looking at two different things, but they're linked together. So this is no longer something that we can use a two-sample hypothesis test on, because these are not independent, right? If we're talking about the size of a tumor before and after chemo, and that tumor's in my body, the before and after are not completely independent. They depend on me and my body and what's going on. So we can't do those anymore. So the question is, how do we tackle something like this? Well, here's the trick. We actually turn it into a one sample set. Okay, so what we're going to do is we're actually going to turn it into a single sample by looking at the difference. So we're going to take those data pairs and actually look at difference. So let's go to that first example of weight loss from an exercise program. So what I would do is I would go to every single person that is in our little group, right? So it's like, okay, Bruno, your weight before the exercise program, your weight after, what's the difference? And I record your difference as my test statistic. And then I go to Lady. All right, Lady, what was your weight before? What was your weight after? Let's look at the difference. Put that in. Right? Ashton, same story. Carson, same deal. So we just go down the list and we look at everybody's before and after. We find that difference, and that's actually our test statistic, or our variable. Okay, so this difference is actually going to be our variable. And then we can use a one sample test on this. So we'll either do a z-test or a t-test, depending upon whether we know the sample or the population standard deviation. Usually we don't. Okay, so it's usually going to be a t-test, but regardless, that's how we tackle this. So kind of a funky thing that we're taking two samples and we're actually bringing it back into one, but it's how we're going to do this. Okay, so let me show you an example. Let's actually take some real numbers here and let's see how this plays out. All right, so for this one, let's say this is what we've got. We're looking at cholesterol levels after taking a new drug. All right, so in this, let's say we've got 6 people. All right, so this first column is going to be the patient. This is going to be their pre-level and their post-drug level. Okay, so we've got patients, we're just going to number them 1 through 6. Because we do have, HIPAA privacy stuff. And before they started taking the drug, here are their cholesterol levels: 210, 235, 208, 190, 172, and 244. Okay, so then they get on this drug, they go through the trial, and afterwards, their cholesterol levels are the following. All right, so as a drug company, let's think about what we are curious about in terms of the null hypothesis and alternative hypothesis. The null hypothesis would be that there is no change. All right, so I'm going to write it in words. The null hypothesis is that there was no change overall. And the alternative, what we're hoping, is that their pre amounts were more than their post amounts. All right, so like I said, what we actually want to do is I'm going to add a third column to this, technically a fourth column, I guess. And what this is going to hold in it is the difference. What was the actual change from before to after? Okay, so patient number 1 dropped 20 points. Patient number 2 dropped 65. Patient number 3 went up 2. Patient number 4 went down 2. Patient number 5 went up 1. And patient number 6 went down 16. And so it's this column that I'm going to do my hypothesis test on. I'm going to look at the differences. So what we should probably do is change our null and alternate hypotheses so that they talk about the difference. Okay, so if there's no change, that means that the difference is 0. So I'm going to use mu for my average difference. And so if there's no change, that should equal 0. Okay. So then the alternative hypothesis, if our before is greater than our after, what should we be seeing in terms of numbers here? If there's a decrease, we're not looking for, is it different than 0? Because if it was different than 0, that could also mean that it went up. That's not what we want to know. We want to just know if it went down. And so this is going to be, we're going to look for where the mean is less than 0, right? So our difference is negative, but there was a drop. Had we been looking for an increase, like let's say this was some sort of a drug that was supposed to increase like muscle mass or something, we'd be wanting to see, is our mean greater than 0 versus just, is there a change? Then it'd be not. All right, so we're going to jump back and we're going to do a one sample test. So the last question, in order for us to do this, is this a Z test or a T test? So what's it going to be here, Z or T? What do you guys think? All right, so Willie just threw in T, and seeing he pretty much speaks for everybody. Thanks again, Willie. All right, I guess we'll go with T. But you should be good with T. It's a T test because I have no idea the standard deviations. None whatsoever. And so without population standard deviation, we've got to go with the T. All right, well, let's see how this plays out. Crack out our calculator and see what we get. All right, so I'm going to go ahead and put this into a list. So I'm going to hit stat, edit, and yeah, what the heck, we'll go to L6, arrow over to L6, and I'm going to put in the differences. So negative 20. Uh-oh. Wrong negative button. So there's a difference between subtract and the negative down here. Negative 20. That's better. All right, so then negative 65 to negative 2, 1, and negative 16. All right, so it looks like we got all those guys in there. That's L6. Thank you for that. Still on the whiteboard as always. Sorry about that. Okay, so again, we went to stat, edit, and I put in negative 20, negative 65, so on down the line. Thanks for catching that, Willie. I appreciate it. All right, so now we're ready to do our test, right? So go stat, arrow over to test. And this time we're doing a T test, right? The T test because we don't know standard deviation. Enter. Okay, this time we're going to input data. So I arrow over. Okay, so next thing, the mean. So what I'm comparing this against is 0, right? I'm trying to see, is the difference 0? All right, so then the list, I need L6, so we'll do second, 6, L6, again, frequency 1. And we are looking for, is our difference less than 0? So I've got it exactly how I want it. I want to see, do we end up getting a negative? All right, so I hit enter, it does its thing. And I get P equals 0.084. All right, so I just went ahead and put that up on the whiteboard. And again, just some other things you can see on there, right? We do have a t-score. We do have our mean. And we also have our sample standard deviation. All right, so come back to the whiteboard. We got our P is 0.0844. All right, so here's my question. Do we reject the null hypothesis, or do we fail to reject the null hypothesis? What do you guys think? Haha, good catch. There is no alpha, right? So that was kind of a trick question. And do we reject or fail to reject? Because we don't know what the alpha is. Always, we need to know what our alpha is in order to respond to this. And what I like about this number is that it's one that could easily be a reject, another one that would be easily fail to reject, depending upon how we've set our alpha. All right. So this is the other reason why alpha needs to be determined before you do your test. Your next project that's due in a couple of weeks. By the way, just throwing that out there to remind you that that's coming. It's 2 weeks away, but it's still 2 weeks away. This one, you're going to do a hypothesis test. So you should probably start getting your group together and start thinking about questions. But when you do this, when you come up with your question, make sure you set your alpha before you do your data. Okay. Because this is sort of bad form. Doing it this way is kind of bad. If I get to this p-value and then I go, oh, okay, well, now I'm going to set my alpha. Because you're kind of letting your data drive your conclusion. And we should already have in mind before we even start how sure we want to be. Right? Think about what that alpha is. Remember, alpha, that's your probability of making a type 1 error. So you need to already be okay with a certain amount of type 1 error just going in. How you determine how, what level that is, that's another story. But you should be going and going, okay, I'm good at alpha equals 10%, or alpha equals 5%, or alpha equals 1%, or whatever. So you should know that first before you go in. Okay. Otherwise, now you're starting to get into some unethical stats practice. This is the kind of thing that gives statisticians a bad name. That and the fact that they're statisticians. And I can say that because I'm a mathematician, not a statistician. But so we should really have that at the start, right? Because think about this one. If we had already stated an alpha of, say, 5%, this would be a fail to reject. And I think that's probably why, Ashton, why you went to fail to reject right away, is because we've been kind of, it's sort of standard to do an alpha of 0.05. But say alpha was equal to 0.1, here we would reject it. So we're in that world of, do we reject or fail to reject? It depends. If this number had been like 0.3, yeah, it doesn't really matter. You'll never see an alpha that big. If it had been p equals 0.08, yeah, that's pretty much an accept, or you reject h naught no matter what, right? So, but in this kind of realm, it sort of matters. All right, so I guess at the end of the day, with this one, with the cholesterol drug, depends how confident we want to be. I will tell you, from my knowledge with drug companies, actually I have a good friend who works for Eli Lilly in Indiana, and Pfizer. He's not a statistician. He's a PR guy. But, regardless, I know for a fact that they are not good with the 10% confidence. They go much smaller. At best, 5%, usually even a little bit lower. So if this were them and these were the results, they would most definitely fail to reject it, meaning they don't think that this drug, that there's enough evidence that this drug actually is decreasing cholesterol level. Okay, at that level of significance. So you got to be careful with that. I like to just throw this example up here to remind you guys, you got to know alpha. If you don't know alpha, that's not specified. This is meaningless. Good, bad, or otherwise. So make sure you always start with an alpha. If an alpha isn't given, assume one, but make that assumption before you run the test. All right, so do you kind of see the idea with these paired, what we do? We're going to look at a difference, and this happens a lot, by the way. There are a lot of, I'm sure you can imagine, lots of scenarios where you're going to want to see, is there a difference? Did we go up? Did we go down? Has it stayed the same? Right? Has there been a change? And regardless, find the difference, and then craft your null and alternative hypotheses in terms of that difference. And then it just turns into a single variable, and we go back and do what we did back in the last chapter. All right, so questions on this one? How are we feeling at this point? All good? All right. I know we actually have a significant amount of time left in class, but I don't want to start the next chapter because I don't want to kind of get in the middle of something and stop. So we're going to call it early today. I owe you some extra time, some other time. We'll call it good. And so just so you know where we are and everything, we are exactly on pace. Everything is doing great. I do want to remind you about a couple of things. We do have our next exam coming up. And I believe that it's a week from today, if I remember the syllabus correctly. And just so you know, that exam is going to cover everything up to and including this chapter. Okay, so this is chapter, I believe, 10. So this exam is going to go up through chapter 10. It will pretty much just pick up where the other one left off, which off the top of my head, I don't remember how far we got. I'll have to go back and look, but I'll let you guys know on Tuesday for sure how far back to go. But you can look at your old exam and see where we left off. But this is going to be primarily things like hypothesis testing for both 2 and 1 variables, setting up confidence intervals for proportions and means. I think the last one, we ended somewhere right around like the uniform distribution. So this will also cover normal distribution, and all the things we've done with that. So I want to say like chapter 7 or stuff, but it's like gonna be like 6 through 10, 7 through 10. I know it might say something different on the syllabus in terms of what's covered. I will double check that, but just want to throw that out, remind you that that exam's coming so you can start working on it now. Also, your next project, that's going to be due 2 weeks. So start getting together with the group. You can feel free to use the same group as last time. Start coming up with an idea. And the other projects, I will have them graded and back to you by next Tuesday so that you can see my comments on them. To be honest, I kind of have forgotten about them, put them on the back shelf. But I will get that stuff so that you can have an idea of how you did on that first one so that you can change things for the next. So feel free to use the same groups, feel free to mix up groups, but think up a scenario where you're going to want to do a hypothesis test and run with it. As always, go ahead and send me any messages or questions. I'll be happy to respond if you'd like some help trying to figure out what exactly to do for your test. I'm more than happy to help you with that. So Lady just asked, is the final going to be a summary of all chapters or just the last ones that we did? When we get to the final exam, it will be cumulative. It will be everything. So yes. But you still have a month to study for the final exam. All right. Any other questions at this point? All right, well, seeing none, I'll just wish you guys all a very happy weekend and enjoy the next few days. And I will see everybody next month. Yeah,
Bruce, is it okay if I stay after and discuss something with you?
Yeah, absolutely.
Awesome. Thank you.
You bet. So I'm going to go ahead and stop the recording then.